Welcome to DAR Tutors for online and home tuition. In this video, we will explore key concepts in IB mathematics, applications and interpretation higher level, focusing on measures of central tendency and spread. By the end of this session, you will be able to, first, calculate and interpret the mode, mean, and median for both raw and grouped data. Second, analyze and determine the range and interquartile range to understand data spread. And third, make informed decisions on which measure of center is most appropriate for a given context. Let's begin by measuring the center of a dataset. This allows us to locate its middle value. There are three primary statistics we use to do this. These are the mode, the mean, and the median. Each one gives us a different perspective on the data's center. Let's start with the mode. The mode is the value that appears most frequently in a dataset. For discrete data, it's simply the number with the highest count. For continuous data, we identify a modal class, which is the class or group with the highest frequency. A key property is that a dataset can be bimodal, having two modes, or even have no mode at all if all values appear with the same frequency. If a dataset has three or more values with the highest frequency, the mode is generally not considered a useful measure of center. Next, let's look at the mean. The mean is the statistical name for the arithmetic average. It's calculated by summing all the data values and dividing by the number of values. The formula is the sum of all x values, denoted by sigma x, divided by the total number of values, n. We use x bar to represent the mean of a sample, and the Greek letter mu, written as m, for the mean of an entire population. Finally, the median. The median is the middle value in a dataset that has been arranged in order from smallest to largest. To find the median's position, we use the formula n plus 1 divided by 2, where n is the number of data values. If this formula gives a whole number, say 7, then the median is the seventh value in the ordered list. If it gives a number ending in 5, like 7.5, the median is the average of the two surrounding values, the 7th and 8th in this case. Let's apply these concepts with an example from your notes. We have the numbers of faulty products returned over a 21-day period. First, let's find the mean, median, and mode for this initial dataset. To find the mean, we sum all the values and divide by the count. The sum of the 21 values is 113. Dividing by 21 gives approximately 5.38. So, on average, 5.38 faulty products were returned each day. Next, for the median, we need an ordered list. Let's arrange the data from smallest to largest. Here is the ordered list. Since we have 21 data points, n equals 21. The median is at the 21 plus 1, 2, or the 11th position. Counting in from either end, we find that the 11th value is 5. So the median is 5 faulty products. This means half the days had 5 or fewer faulty products, and half had 5 or more. Now for the mode. We look for the most frequently occurring value. Looking at our ordered data, we can see that the value 3 appears 4 times, more than any other value. Thus, the mode is 3 faulty products. Now, let's see how these measures change if we add a new data point. Let's suppose on the 22nd day, 9 faulty products were returned. We now have 22 data points. The new mean is calculated by adding 9 to our previous sum, 113, and dividing by the new count, 22. This gives us 122 divided by 22, which is approximately 5.55 faulty products. The mean has increased, which is what we would expect since the new value, 9, is greater than the old mean of 5.38. To find the new median, we again order the data. There are 22 values, so n equals 22. The median is the average of the 22 plus 1, 2, or the 11.5th position. This means we need the 11th and 12th values. In our new ordered list, these are 5 and 6. The median is the average of 5 and 6, which is 5.5. The median also increased, but only slightly, from 5 to 5.5. What about the mode? The original mode was 3. Now, looking at the full dataset, both 3 and 9 appear 4 times each. The highest frequency is 4, and since there are 2 values that occur this often, the new dataset is bimodal, with modes at 3 and 9. This example clearly shows how different measures of center are affected in different ways by new data. Now let's explore the effect of an outlier, or an extreme value, on our measures of center. An outlier is a data value that is much larger or much smaller than the other values in the set. Your notes provide an investigation to analyze this. We'll start with this data set and calculate its mean, median, and mode. The sum is 68, and there are 10 values, so the mean is 6.8. With 10 values, the median is the average of the 5th and 6th values, which are both 6. So the median is 6. And the mode, the value that appears most often, is 6. So for our original data, the mean is 6.8, and both the median and mode are 6. Now let's introduce an outlier. Suppose we add a value of 100 to the dataset. This is clearly an outlier. Let's recalculate the mean, median, and mode. The sum is now 168, and we have 11 values. The new mean is approximately 15.27. Notice how much it has changed, from 6.8 to over 15. With 11 values, the median is the 6th value. Our new ordered list is 4, 5, 6, 6, 6, 7, 7, 8, 9, 10, 100. The 6th value is 7. The mode is still 6. It was unaffected. Comparing the results, the mean was dramatically affected by the outlier, changing by over 8 points. The median increased slightly by 1 point, and the mode was not affected at all. This leads us to a very important conclusion. The mean is the measure of center most affected by outliers. The median and mode are much more resistant to their influence. We will use this understanding to choose the most appropriate measure of center. We have seen the properties of the mean, median, and mode. Now, how do we decide which one to use? The most appropriate measure of center depends on the type of data and the specific question we are trying to answer. It's about context. Let's summarize their key properties in a table, similar to what you'd find in your notes. The mode gives the most common value and is not affected by outliers. This makes it useful for categorical data like shoe sizes to identify the most popular item. The mean is a balancing point of the data. It's the most commonly used, but as we saw, it's highly sensitive to extreme values. This can be a weakness. The median gives the halfway point. It only uses the middle values, which means it's not affected by outliers. This makes it a very robust measure for skewed data. Let's consider some real-world examples. Imagine a shoe store. If the owner wants to know which shoe size to stock the most, the mean wouldn't be helpful. An average size like 7.3 doesn't represent an actual size. Instead, the mode tells them the most frequently sold size. This is a perfect application for the mode. Now consider the salaries of employees in a company. Suppose there's a CEO with a salary of $500,000 and 9 other employees earning around $40,000. The mean salary would be skewed high by the CEO's large salary, making it seem like the typical employee earns much more than they do. In this case, the median would be a much better representation of the typical salary, as it's unaffected by that high outlier. The median would simply be the average of the two middle salaries, which would still be around $40,000. Let's work through an IB-style problem to solidify this. A realtor is trying to convince you to sell your house quickly, saying that the mean house price in your area is $600,000. You investigate and find the recent selling prices. Let's calculate the mean, median, and mode for this data. The sum of these prices is $2,870,000. There are 7 houses, so the mean is $410,000. This is significantly lower than the realtor's claim. The median, the middle value in the ordered list, is $350,000. The mode is not relevant here as all prices are unique. So we have a mean of $410,000 and a median of $350,000. The outlier, the house sold for $800,000, has pulled the mean up from the cluster of other prices. This creates a skewed distribution. In this case, the median of $350,000 is a much better indicator of the price you might expect for a typical house. So far, we've focused on calculating these measures from a list of raw data. In real-world applications, data is often organized into frequency tables to save space. Let's see how to find the mean, median, and mode when data is presented like this. This table shows the number of times a certain value occurred. Finding the mode is very straightforward. The mode is the value with the highest frequency. By looking down the frequency column, we can see that the value 7 has a frequency of 15, which is the highest. Therefore, the mode is 7. Finding the mean is a bit different. The formula has to account for the frequencies. The formula for the mean from a frequency table is the sum of the products of each value and its frequency, divided by the sum of the frequencies. We often abbreviate this as sigma xf over sigma f. To calculate this, we add a third column to our table, the product column, which is x times f. For each row, we multiply the value x by its frequency f. For example, for the value 7, which has a frequency of 15, the product is 15 times 7, or 105. Finally, we sum the product column and divide by the sum of the frequency column. The sum of the frequencies, sigma f, is 40. The sum of the products, sigma xf, is 278, so the mean is 278 divided by 40, which is 6.95. To find the median from a frequency table, we need a fourth column called cumulative frequency. Cumulative frequency is the running total of the frequencies. It tells us how many data points are less than or equal to a particular value. Let's build this column. The first value has a frequency of 1, so the first cumulative frequency is 1. The second value has a frequency of 1, so the cumulative frequency for that row is 1 plus 1, which is 2. The third value has a frequency of 3, so its cumulative frequency is 2 plus 3, which is 5. We continue this process until the last value, where the cumulative frequency will equal the total frequency, which is sigma f, or 40. The total frequency, n, is 40. The position of the median is n plus 1 divided by 2, which is 1 divided by 2, or 20.5. So, the median is the average of the 20th and 21st values. Now we use the cumulative frequency column to find these values. The 12th value is 6. The 20th and 21st values must therefore both be 7. So, the median is the average of 7 and 7, which is simply 7. So far, we have looked at finding the center of a dataset. But knowing the center is only half the story. We also need to understand how the data is spread out. Consider these two statements. The mean height of 20 boys is 175 centimeters. A carpenter cuts 20 planks of length 175 centimeters. Even though the mean is the same, the data sets are very different. The boys' heights will naturally vary, while the planks cut by a machine should be almost identical. This variation is called spread or dispersion. Two common and simple measures of spread are the range and the interquartile range. Let's begin with the range. The range is the difference between the maximum and minimum data values. It's the simplest measure of spread. Range equals maximum minus minimum. For this data set, the maximum value is 5.1 and the minimum is 2.3. The range is 5.1 minus 2.3, which equals 2.8. However, like the mean, the range is highly affected by outliers. For example, if there was a tiny pumpkin weighing 0.1 kilos, the range would increase to 5.0, even though most of the data hasn't changed. For this reason, we often prefer a more robust measure, the interquartile range, or IQR. The IQR describes the spread of the middle 50% of the data. It's the difference between the upper quartile, or Q3, and the lower quartile, Q1. To understand IQR, we need to first understand quartiles. The median splits the data into two halves. Quartiles split these halves into two again. The lower quartile, Q1, is the median of the lower half of the data. The upper quartile, Q3, is the median of the upper half of the data. The median itself is sometimes called the second quartile, QQ. Let's work through an example to see how to calculate the quartiles and the IQR. As with the median, our first step is to order the data. Here's the dataset listed in ascending order. We have 13 data points in total. Part A asks for the median. The median position is n plus 1 divided by 2, which is 13 plus 1 divided by 2, or the seventh value. The seventh value in our list is 5, so the median is 5. Part B asks for Q1 and Q3. Since the median 5 is an actual data value, we ignore it for a moment and split the remaining data into a lower half and an upper half. The lower half is the data to the left of the median, 2, 3, 3, 4, 4, 5. The upper half is the data to the right, 5, 6, 6, 7, 7, 8. Notice that we don't include the median in either half. Now Q1 is the median of the lower halves. The lower half has 6 values. Its median is the average of its third and fourth values, which are 3 and 4. The average is 3.5, so Q1 is 3.5. And Q3 is the median of the upper half. The upper half also has 6 values. Its median is the average of its third and fourth values, which are 6 and 7. The average is 6.5. So Q3 is 6.5. Part C asks for the interquartile range. We simply subtract Q1 from Q3. So the IQR is 6.5 minus 3.5, which gives us 3. The IQR tells us that the middle 50% of the data values are contained within a range of 3. It's important to be aware that there are slightly different methods for calculating quartiles, especially when n is even or when the median is part of the dataset. Your notes provide another example. In this example with 10 values, the notes include all values when splitting the data. The median is the average of the fifth and sixth values, 18 and 20, which is 19. The lower half is then 10, 12, 16, 17, 18, and its median is 16. The upper half is 20, 22, 24, 29, 32, and its median is 24. So the IQR is 24 minus 16, which is 8. The key takeaway is to be consistent with the method you are taught. Let's work through an IB-style problem that combines measures of center and spread. 2 people, Derek and Gareth, recorded their sleep duration for 15 nights. We need to calculate the range and IQR for each person and use them to compare their sleeping habits. Let's start with Derek. First, order his data. Here is Derek's ordered data set. Notice the value 210, which appears to be an outlier. The range for Derek is 450 minus 210, which is 240 minutes. This is a very large range. The median position is 8th. The 8th value is 425. Ignoring the median of 425, the lower half is 210, 380, 400, 415, 420, 420, 425. Its median Q1 is 415. The upper half is 430, 435, 440 plus 5, 445, 445, 450, 450. Its median Q3 is 445. Derek's interquartile range is 445 minus 415, which is 30 minutes. This is much smaller than his range. Now let's do the same for Gareth. Here is Gareth's ordered data. There are no obvious outliers here. Gareth's range is 500 minus 330, which is 170 minutes. His median is also the 8th value, which is 450. His Q1 is 360 and his Q3 is 480. His IQR is 480 minus 360, which is 20 minutes. Now let's compare the results for Part B. Derek has a much lower IQR than Gareth, 30 minutes compared to 120 minutes. For Part C, which measure is more appropriate for consistency? Consistency is about having little variation. In Derek's case, the range of 240 minutes makes his sleep seem very inconsistent. But the IQR of only 30 minutes tells a different story. It shows that the middle 50% of his sleep durations are very close together. The large range is almost entirely due to that single outlier of 210 minutes. By focusing on the middle half of the data, the IQR provides a much better and more robust measure of his usual sleep consistency, showing that he is actually more consistent than Gareth. Finally, let's look at working with grouped data. This is common when data sets are large or individual data points are unknown. With grouped data, we only know that a certain number of data points fall within a given interval or class. We don't have the exact values. The fundamental assumption we must make is that all data values within a class are evenly distributed throughout that interval. Because of this, the mean we calculate is an estimate, not an exact value. To calculate the mean, we must first find the mid-interval value for each class. The mid-interval value, which we'll call x, is simply the average of the lower and upper endpoints of the class interval. This value acts as a representative for all the data points in that class. Let's work through an example from your notes. We have a frequency table showing the ages of bus drivers in 7 different age groups. To find the estimated mean, we'll follow the same process as for frequency tables, but this time, x will be our mid-interval values. First, we create a column for the midpoint, x. For the first class, 21 to 25, the midpoint is 21 plus 25 divided by 2, which is 23. For the second class, 2630, the midpoint is 28, and so on. Next, we create the product column, XF, by multiplying the midpoint by the frequency. For the first row, this is 11 times 23, which is 253. We repeat this for all classes and then sum both the frequency column, sigma f, and the product column, sigma x. The total frequency, sigma f, is 137. The total product, sigma f, is 5161. Finally, we use the formula for the estimated mean. We divide sigma xf by sigma f 5161 divided by 137. This gives us approximately 37.67. Rounding to the nearest year, we can estimate that the mean age of the bus drivers is 38 years. This is our best estimate given the data we have. Let's work through an IB-style problem to find missing frequencies in grouped data. The table shows test scores, but the frequency x for the score of 6 is missing. We'll use the formula for the mean of a frequency distribution, sigma SF over sigma F. We need to express sigma F and sigma SF in terms of x. Let's add the values we know. The total frequency, sigma f, is the sum of the known frequencies, 15, plus the unknown frequency x. The total product, sigma sf, is the sum of the products of known scores and their frequencies, plus 6 times x. Now we can plug these into the mean formula, which we know equals 5.45. This gives us the equation. 545 equals the quantity 79 plus 6x, divided by the quantity 15 plus x. To solve for x, we first multiply both sides by the denominator, 15 plus x. We get 545 times 15 plus x equals 79 plus 6. Next, distribute the 5.45 on the left side. This simplifies to 81.75 plus 5.45x equals 79 plus 6x. Now we gather the x terms on one side and the constants on the other. Subtract 545x from both sides and subtract 79 from both sides. We are left with 2.75 equals 0.55. Finally, we divide by 0.55 to find x. The result is 5, so the missing frequency is 5. Now for part B. Find the percentage of students who passed. A pass is a score of 5 or more. So we need to sum the frequencies for scores 5, 6, 7, and 8. The pass frequency is 5 plus our calculated value of x, which is 5 plus 4 plus 1, giving a total of 15 students who passed. The total number of students is sigma f, which is 15 plus our value of x, making it 20 students. The percentage of students who passed is the number passed divided by the total, times 100. So 15 over 20 times 100, which is 75%. Here's an example of a properly set up MANIM scene using the Content Manager. Now let's add some math. For instance, the probability of event A and event B happening is shown below. Finally, let's clear the content from the page. Thanks for watching this demonstration. Let's move on to the second question, an IB-style problem on grouped data. A factory measures 100 components. The data is grouped into a frequency table. We need to estimate the mean length and the interquartile range. To estimate the mean, we create columns for the mid-interval value x and the product xf. The midpoints are 15, 25, 35, and 45. The sum of frequencies, sigma f, is 100. The sum of the products, sigma f, is 2650. The estimated mean is 2650 divided by 100, which is 26.5 centimeters. Now for the interquartile range, we need cumulative frequencies to find the median and quartiles. The cumulative frequencies are 25, 70, 90, and 100. Since the data is continuous, the median position is n divided by 2, which is 50. We need to find the value of the 50th item. From the CF column, the 50th item is in the 20-30 centimeter interval. We can find it using linear interpolation. Using the formula for interpolation, the estimated median is 20 plus 10 times the ratio 25 over 45, which is approximately 25.56 centimeters. For Q1, the position is n over 4, or 25. The 20th value is the very end of the first class, so Q1 is 20 centimeters. For Q3, the position is 3n over 4, or 75. This is in the 30 to 40 centimeters class. Interpolating, we get Q3 is 32.5 centimeters. The IQR is then Q3 minus Q1, which is 32 minus 20, or 12.5 centimeters. Let's work through another IB-style problem, this time on cumulative frequency tables and curves. We have cumulative frequencies for different age groups. We need to create a cumulative frequency curve and use it to find the median interquartile range and the number of members aged over 55. For part A, we plot the upper class boundaries against the cumulative frequency. We would plot the points 20, 25, 30, 65, 40, 120, 50, 170, 60, 90, and 70 two searches on a graph and connect them with a smooth curve. It's good practice to start the curve at 10-0, since the first class starts at age 10. For part B, we use the curve to find the median and IQR. There are 200 members, so the median is the 100th member. On our curve, we'd find 100 on the y-axis, go across to the curve, and then down to the x-axis to read the median age, which should be around 36 years. For the IQR, we need the positions of Q1 and Q3, which are 50 and 150. Reading from the curve, Q1 is about 28 and Q3 is about 47. The IQR is then 47 minus 28, which is 19 years. For part C, we want to find the number of members over 55. We can find the number under 55 from our curve and subtract from the total. On the curve, 55 on the x-axis corresponds to a CF of about 180. This means 180 members are 55 or younger. Therefore, 200 minus 180, or 20 members, are older than 55. Let's tackle a more complex IB problem involving a missing frequency and estimating spread from a histogram. We have a histogram showing test results. The mean is given as 68. The frequency for the 60-70 interval is missing. We need to find this frequency and then estimate the IQR. From the histogram, we can read the frequencies. The frequency for the 60-70 interval is unknown. Let's call it x. We are given the mean is 68. Part A asks us to show the missing frequency is 56. We'll set up the mean formula as we did before. The mean formula is sigma xf over sigma f. The total frequency is 98 plus x. The sum of the xf products is 65x plus 6540. The mean is 68. So we have the equation C8 equals the quantity C310 plus 65x, divided by the quantity 98 plus x. Now we solve for x, distribute the 68, regroup the terms, and solve to get x equals 56. The frequency for the 60 to 70 interval is 56 as required. Let's re-examine the calculation for sigma xf. 10 times 35 is 350. 12 times 45 is 540. 22 times 55 is 12-10. 38 times 75 is 2850. 16 times 85 is 1360. Summing these constants, 350 plus 540 plus 1210 plus 2850 plus 1360, 63 on 10. The sum sigma f is 10 plus 12 plus 22 plus 3, 8 plus 16, x 98. The setup is correct. This leads to x y 118, not x of 56. The problem statement itself seems to have a typo or inconsistency. Since a negative frequency is impossible, the given mean of 68 is incompatible with the rest of the histogram data. In an IB exam, you would flag this error and state that a valid solution does not exist under the given conditions. Let's assume for the sake of the problem that the frequency for the 60 to 70 interval was intended to be 56, and we were asked to show this. If x are 56, then sigma f equals 98 plus 56 equals 154, and sigma xf equals 6310 plus 65 to 56 equals 6310 plus 3640 equals 9950. The mean would be 9950 at 154, which is approximately 64 per 6. This is not 68. There is a fundamental error in the problem. For part B, estimating the IQR, we'll proceed using the calculated frequencies from the histogram. Total frequency n is 154. We need the 38.5th value for Q1 and the 115.5th value for Q3. These fall into the 50 to 60 and 70 to 80 intervals respectively. Using interpolation, Q1 is approximately 53.9 and Q3 is approximately 71.9. The estimated IQR is 18. This is a higher level skill. involving careful interpretation of the histogram, formula use, and algebraic manipulation. The error in the problem highlights the critical need to check for consistency in data. Here is our fifth and final IB-style practice question. We are given a frequency table for the number of children in 59 families. We need to find the mean, mode, and median. Let's build our calculation table. The total frequency, sigma f, is 59. The total product, sigma xf, is 134. The mean is 134 divided by 59, which is approximately 2.27 children per family. The mode is the value with the highest frequency. This is 2, with a frequency of 28. For the median, we need the 30th data point. From the CF column, this falls within the group of families with 2 children. So the median is 2. The question also asks how this school compares to a national average of 2.075 children. The school's mean is higher at 2.27. This suggests the families at this school tend to have slightly more children than the national average. We've covered a lot of ground today, from the basic definitions of mean, median, and mode to their application in raw, grouped, and cumulative frequency data. Let's quickly review the key objectives we set out to achieve. First, we learned to calculate the mean, median, and mode and saw how outliers affect them differently. Second, we defined and calculated the range and the more robust interquartile range to measure the spread of data. And third, we discussed the importance of context and outliers when choosing which measure of center best represents a dataset. We used several IB-style practice questions to reinforce these concepts. For further practice and detailed explanations, you can visit our website at dartuters.com.